Okay, we already finished until this section on Monday. So you learn about two metrics. The first metric is the elbow method, and the other metric is silhouette score. For the elbow method, it is based on the elbow or the lowest these things. So it can be 2 or it can be 3. In this data set, we choose 2. And if we look at the performance of the silhouette score, the range will be +1 until -1. So +1, it is good clusters. -1, it can be misclassified, or the cluster result might not be in the correct groups. So if it is +1 or nearby +1, it is better. If it is nearby -1, then it is bad. Based on the result, the silhouette score with k equals to 2 is the best. So when k equals to 2, we can see this value is 0.7 something something. So the silhouette score, we choose k equals to 2. And for the elbow method, we choose k equals to 2. Then in this data set, k equals to 2 is the best. Or if we create two groups for the smartphone data, then that is the best performance. When we measure the cluster's quality, there will be two kind of measures, or there will be two kind of methods. The first is intrinsic, and the other is extrinsic. Intrinsic method means it is really unsupervised. What is unsupervised? Because this is PG2 workshop, because no label data. So the ground truth is unavailable. There is no ground truth. There is no actual label. For the extrinsic, it is supervised. So actually the ground truth is available. We have the actual label, but we want the machine learning to see whether the clustering result, whether the clustering, it is the same with the actual label or not. So let's look at one by one. The intrinsic. Intrinsic means we are going to evaluate the goodness of a clustering by considering how well the clusters are separated and how compact the clusters are. We use the silhouette coefficient or the silhouette score, what we did previously. Usually we use that kind of score to check the quality of the clusters. But for the extrinsic or supervised, we need to check with the ground truth, because we have the ground truth or we have the actual label. Compare a clustering against the ground truth using a certain quality measure. So today we are going to learn one matrix, which is run index matrix. Clustering quality, it means we are going to check the clustering result. This is the clustering result. And CG is the actual label, or we call it ground truth. So we have a clustering C, we compare with the CG, the ground truth. Now let's see. If we do with the clustering, we don't have any label. Now I change the data a little bit. Suppose we have a label. Okay, this is an example. I have the data about the camera, how many megapixel, and the data about battery, how many hours that the smartphone lasts. So the data here shows that the first smartphone, it has 48 megapixel, 22 hours for the battery, and the status is premium. The second smartphone, the camera is 30 megapixel, the battery is 14 hours, and the status is premium. The third camera, the third smartphone, the camera is 18 megapixel, it has 14 hours of battery, and the status is just a general phone, ilban phone. Then we can plot. So this is the plot. Okay, this is the premium phone, and this section is the general phone. Okay. It means this is the label, or we call this is the actual label. So using this actual label, now I want to perform the clustering. If I perform clustering, I want to check the performance. So checking the performance result means I want to compare the clustering result with the actual label. Now, for example, after I do the clustering, so this is the result of clustering. Okay, this is the result of the clustering. And then this is the result from the actual data. If you look at this one, the blue color, okay, 1, 2, 3, 4, it belongs to cluster 0 or class 0. So you can see here, orange, 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 and orange. So if you look at this, in the actual data, 1, 2, 3, 4, 5, they are in the one group. Okay, so this is the actual data. But the result of clustering, it shows only 4 data. 1, 2, 3, 4, which is in the cluster 0. Now let's see this actual data. We have 1, 2, 3, 4, 5 of the premium phone. And what about this? This is cluster 1. We have 1, 2, 3, 4, 5, 6. Okay, so there are 6 of cluster 1 and there are 4 of cluster 0. Meanwhile, in the actual data, we have 5 general phone and we have 5 premium phone. Okay. Now, in this case, we need to check the performance. So how good is our clustering? So in this result, we can see this data is somehow not representing the actual. In the actual, it belongs to this group. But this data, the clustering results show that it belongs to this group. So there is a mismatch. Okay, we call this is mismatch sometimes. It should be here, but the clustering shows that it belongs to the other group. So it indicates there is one data on which the actual data is different from the clustering result. Then, yeah, we need to check the performance. How to check the performance? So we need to check the correctness between the actual data and the clustering result. So note that we can use similar to confusion matrix. Do you still remember? Confusion matrix. In the confusion matrix, we have the actual compared to the predicted. Okay. Now we are going to check the actual data compared to the clustering result. So this predicted is the clustering result. We want to know when the actual data is general, how many of them belongs to cluster 0? Okay, the general, 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 and 1, 2, 3, 4. Okay, there are 4 data belongs to cluster 0 and 1 data belongs to cluster 1. What about the premium? So you check the premium, 1, 2, 3, 4, 5. And how many of them belongs to cluster 0? So this is 1, 1, 1, 1, and 1. Then all of them belongs to cluster 1. Then we can see this table. For the general phone, 4 of them belongs to cluster 0 and 1 of them belongs to cluster 1. But for the premium, all of them belong to cluster 1. And among of them, there are 5 general phone and there are 5 premium phone. For the cluster 0, we got 4 data, and for the cluster 1, we got 6 data. So in total, we still have 10 data. We can use the RAN index. There is another measures, we call it adjusted RAN, but I will not explain this one. Yeah, if you want to study this one, yeah, you can look at other literatures, but today I'm going to focus on RAN index. RAN index tells the arbitrary nature of cluster labels in unsupervised learning. What is arbitrary? Arbitrary means something random. We do not know. So whenever we have this data, general, we do not know whether it belongs to cluster 0 or cluster 1. It is arbitrary, random. Maybe actually the general should be in the cluster 1 for all. It is lucky that most of them are in the cluster 0. If you look at the premium, most of the data belongs to cluster 1. Okay, we can say that this is fully correct. But for the general, still there are some possibility. It might be belong to cluster 0. It might be belong to cluster 1. And we do not know whether cluster 0 represents the general or cluster 1 represents general. That's why we call it, this is the arbitrary nature. It's random nature. Okay. Because the unsupervised learning, we assume we have no label. So this is just a metric to check whether the result from the clustering is good or bad. So we need to measure the RAN index. The RAN index means A plus B divided by N combinatorial 2. A represent the correct similar pairs, B represent the correct dissimilar pairs divided by the total possible pairs. We call it pairs. Pairs means we want to check one example. So this is one example or one instance compared to the other instance. You want to check this instance compared to the other instance, and so on. Now let's see how to calculate the RAND index. The RAND index, as you see, the formula is this one. We can check the correct similar pairs and we can check the correct dissimilar pairs divided by the total possible pairs. What is the total possible pairs? It is a formula n2, or we call this is the combinatoric of n, comma 2. C means the combinatoric. Or sometimes we call it combinatorial. Okay. And we want to check n, which is the number of data, and we want to make the pairs. So the number of data, we have 10. Okay. So the total possible pairs, because it is the combinatorial n and 2, it will be n multiplied by n minus 1 divided by 2. So this is the combinatorial. I'm not sure with the Korean word, okay? So you can check the combinatorial. So this is the formula, n multiplied by n minus 1 divided by 2. Then we can get 10, which is the number of data, multiplied by n minus 1. N minus 1, it means we have 9 data after we minus with 1, divided by 2. So there are 45 pairs. There are 45 pairs. So what does it mean by these 45 pairs? So I give you a visual representation. So like this one. This is data number 1. This is data number 2, data number 3, data number 4, 5, 6, 7, 8, 9, 10. So this is data number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many total pairs do we have? If you look at this combination, there are 10 multiplied by 10. Okay. So 10 multiplied by 10. So the total here, there are 100. Okay, there are 100. There are 100 cells of this one, but we do not consider this one. 1 and 1, so we do not consider that pair. 2 and 2, we do not consider that one. 3 and 3, we do not consider. So this diagonal, we do not consider it. And also, we do not consider this lower triangle. It means from 100 items, we will consider only the upper triangle. The upper triangle means we have 100. We will minus with 10. 10 is the diagonal. And then we will also minus with this one. So this one means we have 45. So we have 45 at the upper triangle, and we have 45 at the lower triangle, or the easy words is we just consider only the pair between 1 and 2, but not the reverse, not 2 and 1. So we just need to know, is there any relationship between 1 and 2? Is there any relationship between 1 and 3? Is there any relationship between 1 and 4? Is there any relationship between 1 and 5, and so on? Then the total of this combination, it will be 45. Okay. Now let's get back. So we have the total pairs, there are 45. Now I want to check how many of them are correct for the similar pairs. For the similar pairs means if they are general phone, we have 4. Okay. In the general phone, there are 4 which is correct. For the premium phone, there are 5 that are correct. Then in total, we can use again the combination for multiply sorry, yeah, 4 multiply by 4 minus 1 divided by 2. Then it will be 4 multiplied by 3 divided by 2. Then we have 6. So the general phone, if you see this one, this is data number 3. This is data number 4. This is data 5, 6, 7. This is data number 8. And this is data number 10. Okay, so 3, 4, 7, 8, and 10. Then we can check the data 3, 4, 7, 8, and 10. For the general phone, we have 1. So 3 and 4, this is a pair. 3 and 7, okay, they are matching. Okay. 3 and 8, they are matching. And then 4 and 7, 4 and 8, they are matching. And we have 7 and 8, they are matching. So in total, we have 6 pairs. 1, 2, 3, 4, 5, 6. Now, let's see the premium phone. What is the premium phone? The correct similar pairs, there are 5. Then we have 5 multiplied by 5 minus 1 divided by 2. So it is 5 multiplied by 4, 20 divided by 2. Then there are 10 pairs. So you can check from data number 1 and 2. Okay, they are similar and they are correct. 1 and 5, they are similar because both of them, they are in the premium and they are in the same clusters. 1 and 6, they are premium and they are in the same clusters. 1 and 9, they are premium and they are in the same clusters. Okay. So we can check those in the orange color. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10. Oh, I think sorry. I make this is the opposite. The G is 6, P is 10. Okay. P is 10, G is 6. Okay. I'm sorry, I put the wrong numbers. But at the end, the total is 16. It means we have 16 of the data, they are correct and they are in the similar state. This is general in the cluster 0 and this is also general in the cluster 0. this is general in the cluster 0, and the data in 7, it is general also in the cluster 0. So we calculate all of them, and there are 16 pairs. We call it there are 16 pairs that are correct and similar. So correct and similar pairs. So this is from 4 and 5. Now let's check the correct dissimilar pairs. What does it mean? For the correct and dissimilar pairs, we want to check this is 4, this is 5, and we have 4 multiplied by 5, which is 20. So how can we get this 20? If you look at this one, the premium, the data number 1, it is correct. This is correct. Data number 3, it is also correct, but it is dissimilar. What is dissimilar? The data number 1, it is premium, and the data number 3, it is general. Okay, so they are not in the same data, they are not in the same actual data, but they are correct. Why they are correct? Yeah, because this one, the data number 1, it belongs to the data number 1 belongs to cluster 1, and the data number 3 belongs to cluster 0. So they are totally in the different cluster. So you can see the yellow color. Now let's see if we want to see the data number 1 and number 4. The data number 1, it is in the cluster 1. The data number 4, it is in the cluster 0. Then it is dissimilar. It is dissimilar because data 1 is P and data 4 is G, and they are split. The data 1 is in the cluster 1 and the data 4 is in the cluster 0. Okay. So you can calculate the number of yellow. Here I put the yellow one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are 20. It means, yeah, for the data in the premium, which is correct, we have 5, and for the general, which is correct, we have 4. Then we have 20, where the 20 pairs, they are correct, but they are dissimilar. Now, the remaining part is the white color. So what is the white color? The white color is the one that is not correct, and this is also not similar. So if you look at this one, the data number 1 and the data number 10. The data number 1, it is premium and in the cluster 1. Data number 10, it is general and the cluster is 1. So they are actually in the same cluster, but the actual data is different. So we don't consider it as correct. Data number 2 and data number 10. Data number 2 and data number 10. So it is the same. Data number 2, actually it is premium and it belongs to cluster 1. However, the data in the point 10, it is general and it is in the cluster 1. So they are in the same cluster 1, but actually they are not the same neighbor. So we put all of this one as a white color, or this is the incorrect pairs. So the red index means we want to see the correct part here. We have 16, And the correct dissimilar pairs, we have 20. So the correct similar pairs, we have 16. And the correct dissimilar pairs, we have 20. And we will divide with the total possible pairs. So the total possible pair is 45. Then the result is 0.8. Then we can say that the clustering quality for this data set is 0.8. This is based on the trend index. Yeah, you can look at this one, and you can try to, if you want, you can review what does it mean by the P1, G0, and etc. When you use k-means, there are some limitations. First, the k-means is applicable only to object in a continuous n-dimensional space. What does it mean by continuous? It is the numerical value. Okay. So the data, if it is numerical, then you can do it. But what about if the data is categorical? If the data is categorical, yeah, if you change from the categorical to numerical, it also still have some issues. We cannot get a good cluster because when you transform the categorical into numerical, most probably you will use 0 and 1. 0 and 1. For example, if you use the one hot encoding, you have only 0 and 1. Or if you use the label encoder, you have 0, 1, 2, 3, and so on. So in some cases, this kind of number can make the issue for the clustering. That's why the k-means, it is working well when all the data are continuous. We need to specify the k. As you know, we need to use the elbow method, and we need to use the silhouette score. This is the metric to determine the k. But sometimes we can determine our own k if we know the domain of the data. So we need to specify k, the number of clusters in advance. This kind of k-means is also sensitive to noisy data and outliers. So if the data has some outliers, it will make the clustering result becomes bad. And it is not suitable to discover clusters with non-convex shape. What is non-convex shape? This is non-convex shape. So the shape will be always good, like this one. So if you have data like this one, okay, for example, so the data, when you do the grouping, you always do grouping with the convex shape. You cannot do, for example, you cannot do the clustering with something like this one. You cannot do clustering like this one. Okay, because non-convex shape is not available for k-means. So we need to use another method in order to produce like the blue color grouping. So let's look at this problem. When we do the clustering, there might be some other approaches. What we learned at the first section, it is about the partitioning approach. Partition. Partition means we construct various partitions, then evaluate them by some criterion. So we already look at the minimum of the sum of square errors. So you learn about the WCSS within cluster sum of square. And yeah, we evaluate if the value is the lowest or in the elbow, then it will be the best key. This works for the k-means, and there are some other variants, for example, k-matrix, Clarence, and etc. So we have the data like this one, and then we want to make a kind of group. So you can see the grouping is always convex, 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 convex. There are another approach, we call it hierarchical approach. It is to create a hierarchical decomposition of the set of data. And there are some criteria. There are methods, they call it Diana, Agnes, Birch, Chameleon. So this is the example. So you can make a kind of tree. So you can make a kind of tree, and then we can make a cutoff. For example, I want to make 2 clusters. Then I can split here. Okay, the cluster 1 is P and Q. The cluster 2 is R, S, and T. Or if I want to make 3 clusters, then I can make something like this one. The cluster P, Q, and then R, and then S and T. So there will be some criterion to make the clusters based on this hierarchy. The other kind of clustering, we can say it is based on the density or density-based approach. The density-based approach, it is based on the connectivity and the density function. So if you look at this one, the shape is like a kind of moon. If you do with the k-means, you will get like this one. So the color red, it is one group, and the color blue is another group. Actually, we know from the shape. From the shape, is not red and blue like this one. It should be blue and red like this one. We can use the DB-scan or optics or DenGlu to get the grouping like this result. So let's just focus on the partitioning. At the end, maybe I will give you one example about the hierarchical. Now let's try to do the clustering with the examples that we usually use, which is the IRIS dataset. We know that the IRIS dataset, it is for supervised. Okay. The supervised means we have the data with label. So we already know that this data belongs to Setosa. This data belongs to maybe Virginica. This data belongs to maybe Versicolor. So we have the label actually. Can we do clustering with this kind of data? Actually, yes, we can do. If you still remember, for measuring the clustering, we have 2 methods, intrinsic and extrinsic. When we deal with the intrinsic, it is really unsupervised. So we really have no label on the data. But the extrinsic means it is the supervised, where the data has the actual label. Now with the IRIS dataset, we can perform the clustering. And before we perform the clustering, we can remove the label. So you know, when we do the data pre-processing, we can remove the column. And after we remove the column, we can perform the clustering and compare the clustering result and the actual label. So we can use the RI or the RAND index to check whether the clustering is good or not. So we can perform both of them, intrinsic and extrinsic. For the intrinsic, we can perform the silhouette score. We can perform the silhouette score and also the elbow method for the intrinsic. For the extrinsic, we can perform the RAND index. So let's see how we perform those things in the section. Whenever you have the data, and let's say the data is already in the good format. In the good format means we have no missing value. And let's say no outliers. That's why when we do the team project, I will ask you about the EDA. Why EDA is important? Because in the EDA, we can see, is there any missing value on your data? And then is there any outliers in your data? So we need to check this one before we do the machine learning. And also, we can check how many data, how many columns will you do for the analysis? How many rows will you use for the analysis? This will also affect the result. Now we are going to check the iris dataset, and we know that all the data are in the numerical. You can see the sepal length, sepal width, petal length, petal width. They are numbers, 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 numbers. Suppose I'm going to do with the normalization. Okay. So you already know normalization. There are two kind of normalization. We have min-max normalization, and we have the Z normalization, or sometimes we call it the standard scalar. So the standard scalar means we want to check based on the mean and the standard deviation. I'm going to use the standard scalar for this example. I'm applying the standard scalar, and then let's fitting the standard scalar to the iris data where the species will be dropped. So you will drop the species. It means you will not use the categorical value. So we do the data pre-processing. Yes, suppose we normalize the values before we perform the machine learning. At the end, because we need to measure the performance, the clustering performance, we need to check with the RAND index. What is the RAND index? We need to check the clustering with the actual label, because we need to check the clustering with the actual label. So after we do the transformation into the standard scalar, let me put again into a data frame, and then let me concat. Do you still remember concat? This is to combine. Okay, concat. This is to combine. So concat is from the concatenation. It is to combine. What is the combination? It is to combine the scaling data with the species data. So I put again the label because I need to calculate the RAND index later. After that, we can run the clusters. So let's suppose I'm using the k equals to 3. And let's use only the data like this. So let's use only the numerical features. So I don't use the categorical features. And then let's get the cluster tables. And then let's print the centroid. Then we can see the overview of the clustering result. This is the clustering result. And this is the actual data. The actual data, you know, we have 3 flowers, Setosa, versicolor, and Virginica. After we do the clustering, we have cluster label 0, cluster label 1, and cluster label 2. Okay. And you can see cluster label 0 is the light color, cluster label 1 is the purple color, and cluster label 2 is the black color. So you can see that some of them are mixing in the actual data, but the clustering result shows quite good. Okay, let me stop here. Let's have a break. I will continue after the break.